Good morning, good day, good evening, good night, my fellow listener, and thanks for dropping by on my first lecture regarding diffraction effects. And of course, the course is still optics, as it has been for the last few weeks. So as we can see, it's quite encouraging. We're almost there regarding the course table of contents. So not much is actually left regarding your studies. So I hope you're feeling positive about this. And the next lectures that I will be having, well, essentially I will be speaking about diffraction effects. And in a nutshell, it's exactly the same thing mathematically that we were done in the previous chapter regarding interference effects. But now instead of discrete summation of fields, wavelets, rays, we now are thinking that we in fact have a continuous distribution of wavelets that we are summing. So essentially we are moving away from discrete sums into integrals. And along the way, what we will do here in the first lecture, I will be introduce and apply Huygens principle to understand diffraction of light. And especially we are trying to understand how diffraction takes place when we have a small aperture right now of an arbitrary shape. And we want to see what happens for light when it's propagating through this small aperture. Roughly of the order of a wavelength, so that we actually are seeing visible diffraction effects. And qualitatively, of course, in the first lecture, I will be trying to point to you that what happens is that the diffracted field far away from this aperture that is small in size compared to the wavelength, essentially this diffracted field is a sum of all spherical waves scattered through or scattered by the aperture. So this is basically where we are applying the Huygens principle here in our situation. And at the end of the lecture, I will introduce two different regimes of diffraction that really give rise to different mathematical formulations to understand diffraction problems. And then in the second lecture, I will be focusing more on the Fraunhofer diffraction, so-called the far field approximation of diffraction. And there I will be basically solving the general diffraction integral. I will be soon introducing to you in this lecture under the approximations that we have, so that we are assuming that our location of interest into which we are looking at the diffracted fields, that's far away from our aperture. And now, at the end of this lecture, I will give two different physical and mathematical interpretations of the resulting in simplified Fraunhofer diffraction integral. So good stuff on the way, because mathematics is involved and Fourier transforms will be involved at the end of that lecture. And then in next lecture, diffraction from the basic apertures for shapes, I will apply Fraunhofer diffraction integral into three different simple shapes, aperture shapes. So basically a single slit, a narrow in width, a rectangle, and then a circle. And I will calculate their diffraction profiles, their irradiance profiles, and basically we will learn how light is being diffracted by that kind of apertures. And then in lecture 4, I will extend my treatment into diffraction from multiple slits. So essentially we will generalize our treatment of a single slit into several slits that are now periodically arranged in a given direction, and this essentially give us a math to understand how diffraction gratings behave. And then finally, I will be speaking more about diffraction gratings as optical components that provide us means to do, for example, separate different frequency components of incident light into different directions and so forth. So highly useful optical components that provide functionalities that cannot be easily achieved by using other components, for example, lens. Of course, prisms, they in a way are competing against diffraction orders or competing with diffraction orders, so that they also can be used to provide same kind of optical functionality. So essentially dispersing different frequency components into different directions. So this is what I will be speaking about in my next 5 lectures. And now I will start my first lecture regarding the basic theory. So here we start. So we apply now the superposition principle, as we have so bravely applied in previous lectures. And now instead of operating on a discrete distribution of wavelets or fields or sources, we now are thinking that we in fact have a continuous distribution of sources or waves that they give rise to a phenomena of diffraction. So now the phenomena, we do not call them interference phenomena anymore, but rather diffraction phenomena. And essentially the difference here between interference effects is not really the mathematical treatment as much, but rather in the kind of how many waves we are summing together. And of course, in a way, mathematics is changed so that we are not now calculating discrete sums, but rather integrals of rays, waves, or sources scattering light or emitting light. So basically, the situation is like this. So we have an incident wave, and then we have some kind of slit, aperture, some kind of shape that is obstructing light of propagating through in some areas, and then on the other areas, light is actually being propagating through. And now we want to understand how the diffracted field, total field, looks like in here. And essentially, we need to sum over all of these possible contributions that the rays of light are propagating through different locations from the slit. And this is, as I said, very much the same kind of mathematics as in our earlier chapter regarding interference, but there we were dealing with discrete distributions and series mathematically. And now the kind of physical starting point for understanding diffraction is that we start considering the Huygens-Fresnel principle, which essentially states that every point of a wavefront, so that would be the diffracted wave in here, on there, on the kind of object space or image space would be maybe a better word here. There, each of these points essentially acts as a source of new wave. And now when we are applying the same principle into the field in here, we see that, okay, like each of these locations of a wavefront hitting this aperture location, this slit here, then each of these locations acts as a point of a new source of a plane wave. Sorry, not a plane wave, but a spherical wave. And this is the kind of principle that we will apply, and it has been known for mankind for a long time. So essentially, this is not actually a new piece of mathematics we're dealing with. So now we have a new wavefront. Basically, we should consider in each of these locations nearby the slit. And this, like a new wavefront that we then subsequently are giving rise to, or that emerges after fields being diffracted by the slit, that is essentially a superposition of new waves. And since now we don't have a kind of discrete number of locations, but rather it's a continuous variable, it's like a continuous distribution of openness here on the shape. We are not summing things, but rather we are performing an integral, which of course to a physicist is essentially a little bit more sophisticated summation than just a discrete sum. So let's start the mathematical treatment, and let's start by considering a wavefront of a wave. And the wave, let's denote that as an EA, A as an aperture, that is incident on the aperture function or aperture slit. So physically really something that is blocking propagation of light in some regions, and only in a tiny region that is roughly of the order of wavelength in open size is where light actually can propagate through the slit or aperture. And now we're interested in how the field looks like in a far field point, denoted with a capital R position vector. So this essentially, this entity, this position vector is here, somewhere far away. And the small coordinates we restrict to using variables in here, position vectors in hereby. So the capital R, Z, and Z, they correspond to the far field locations, and the small variables, they correspond to the locations nearby the slit. And then based on the Huygens-Fresnel principle, essentially a new spherical wave originates from each of these points R prime, and R prime is now essentially a point in the location in the plane of this aperture of this slit. So R prime is now my position vector here, and this is how we start the mathematical treatment. And then we have a spherical wave originating from this point, and of course this wave will be of form. We are interested in the far field location, so capital R location, how the field looks like. And then we have some kind of starting amplitude EA, and I think I should have actually R prime here as my argument, because in principle, of course, this guy could vary in amplitude in these different locations. So sorry about the sloppy notation here. So this is should not be just a scalar radial position or distance point between the points R prime and capital R, but rather it should be the R prime vector in itself. Okay, so we have a spherical wave, so we must divide the amplitude with R, and R is now the distance of point r prime from r. So we are really having a spherical wave. And then we have the phase accumulation exponent ikr. And this is not my sloppiness here involved, but rather these should be scalars. Like, please don't divide things with vectors. Most of the time, you could get something awful and confusing out. And in here, this phase function would be something that gives us a phase function of a spherical wave. So this is perfectly fine. Let's not put vector k and r here, but rather just things like this, so that we really have a spherical wave here mathematically. So this is our single spherical wavelet originating from a point of a r prime at our aperture function. And now r is the distance of a point r prime from r, and the treatment here we only do for a single monochromatic field. So we just assume that we are dealing with a single frequency component, and we do not generalize the situation into polychromatic fields. Of course, we could do that, but here we want to just qualitatively and conceptually understand diffraction effects. We do not need to deal with different colors as such. But of course, you know how things would be generalized into that direction. We would just need to sum over different frequency components, and that's it. Especially if you would be familiar with the Fourier transforms, you would know right away that now we are in a so-called frequency domain approach, so that we are not considering as such time-varying fields, but rather we are considering a single frequency component. And then, of course, it would be quite easy to generalize the math into time domain and polychromatic fields. So time domain, time-varying fields. Okay, so we have the total field at the observation point capital R, and then how we want to calculate that is that we don't sum, but rather we integrate over all the spherical waves that are originating from the small areas that we break our aperture into. So essentially, I will now have a function S that describes the shape of my aperture, and then ds is the differential of this aperture shape. So a differential of an area cross-section. So the total field now is basically an integral over this shape function, and then we are integrating these different spherical waves, and then we are integrating over ds here. So essentially, this guy is changing slightly when we are doing things, so that depending on where we are, the amplitude might be changing. And of course, it's the aperture shape that matters here, so that when we actually are having like propagating through the slit or the aperture. So the trouble here is that even though this looks very simple, like we cannot really analytically easily integrate this, especially in the case of an arbitrarily shaped function, so arbitrarily shaped aperture. So this is somewhat problematic. But the nice thing here is that it's quite intuitive from the physical point of view, and it really nicely illustrates us how the problem looks like. So essentially, like with the problem here is that how we could approximate the distance r, and now the scalar r, so the modulus of capital R minus r prime. And then the question mark would also be, what is the smartest choice of coordinate system to be used to describe the aperture function S? So these essentially are the kind of two problems at hand. It comes to mind that how we can simplify this integral. And of course, conceptually, this is quite nice. So essentially, we are integrating different spherical waves originating from a slightly different locations in the aperture. So physically, this is quite clear and really complies with our starting point of applying Huygens Fresnel principle to our scenario. So we have diffraction integral that looks exactly like this as before. And only we can solve this analytically in two simple situations. And we will be dealing the second one later. And the first one would be when the observation point R is only a some distance away from the aperture S. So basically when the R, the distance from the scattering point into the observation point. So R is larger than wavelength, but not much so. And then this case would give rise to a Fresnel diffraction. And even though we would be able to solve things analytically, this is beyond our scope. But I think still in the laser physics course, or at least in Orazio Svelto laser physics book, there is some kind of treatment of Fresnel diffraction. And of course, in our book of Hecht, we will have some treatment of that, so that you can look more details from there. but we just say that this is Fresnel diffraction is something that is beyond our scope of working out on an introductory level course on optics. But nevertheless, in some cases, we would be able to solve the situation and how the diffracted field would look like somewhat nearby the aperture. So even though we would be further off than a wavelength from the aperture, we would be still somewhat close to it. And this would be the kind of complicated regime for us to operate, mathematically involved. So we do not deal with that here on this course. But rather, we only consider a situation when the location point of interest, is actually far away from the aperture, so that now the scalar R is much greater than the wavelength. And this is now the regime that we know and call as a Fraunhofer diffraction. And this is also known as the far field approximation. And this is essentially where I stop. And I will stop by saying that we are now interested in calculating the diffraction integral. This guy, please remember the formulation and where it arises from. And then we are interested in calculating that when we are far, far away from the aperture. So essentially this condition applies. But more on Fraunhofer diffraction, of course, in the next lecture. So let's not get ahead of ourselves. So I thank you for listening my monologue again. You're a very brave soul of continuing to do this. And thanks for listening, and please join me soon when we are actually lecturing and listening, hearing and learning about Fraunhofer diffraction. So thanks, and bye-bye.